So, final thing, somehow an application of these first passer times to encounter times. So, and I'm going to show you a paper that we just submitted. It's in review now. I mean, it's very physics-like, but I'm going to tell you the interesting things, and it is related to first passage time. And so, what is first passage? You heard me. I was talking about there is a source, which is what is called the source is the animal, so an initial position, and there is a target, which is static. Now, suppose the target is not static. So things, of course, as you can imagine, get complicated, no? But not too much, in the sense that what happens is that if you have this, which is your source, your animal, and this is a target, and now this is moving, and this is also moving, then essentially, mathematically speaking, you go to a higher dimensional space where in those simple cases where both are random walkers, then essentially you have a random walkers in 4-dimensional space. So this is moving and this is moving in 2 dimensions. So you go to an object which has 4 coordinates, and then you start asking questions about this object in these 4 coordinates, so how much time it takes to, for example, be in certain positions, so on. And what are these certain positions? The meeting place. So now your target, it's a complicated object because you have to take into account where are all these possible meeting places, which, imagine they are in a finite domain, and then the entire finite domain in 2D is a meeting place. So then you have to map this into a 4-dimensional space, and the finite number of data, imagine it's a lattice, the finite number of places where they can meet has a certain shape, quite complicated. It's yet unclear to me.
Why 4D?
Well, because you have 2D coordinate here, random variable, 2D coordinate here, random variable. Now, if I just follow over time these processes, which are these independent processes, it's a random variable with 4 coordinates. So it's another random walker if you want, if they're both moving as random walker in 4-dimensional space. But the point is that where they meet, you'll see that now what I've been able to solve and explain you, it's a 1-dimensional problem of territorial animals with overlapping home ranges. Let me finish, which is quite complicated in the way you see where the targets are. But I'm just telling you, the general problem is this, nobody knows the solution to this problem yet. But this I can say stay tuned because it's quite complicated. But this is where I'm aiming from. Try to find general solution to this problem. How do you actually find the mean encounter time for these 2 animal moving? So why is it important? Well, we all know, as animals meet, they are for different reasons, sexual reason, and then it's important also for understanding how epidemics propagate and so on, because as they meet, they pass infections. So it's pretty important. Predator prey, so there are a variety of reasons. Oh, the speakers. So although this is a general problem, which I don't know yet how to quantify, I'm going to tell you a problem which is simpler, which is a 1-dimensional case, complicated enough, but it has a very practical application, which is a propagation of disease in a territorial population. So sorry, I interrupted you because I wanted to finish. You were going to ask.
You answered.
Oh, I answered. Oh, I'm very good then. Okay.
Yeah.
So, okay, yeah, I can just. So, what is a problem that we look at is that you have a 1-dimensional space, if you're an infinite 1-dimensional space, and you have animals, as you know, that I always draw as like this, and then this is an animal within its own home range, and then you have a neighbor with which there is an overlap, and I hope you understand what I'm going to do here graphically, and there is I mean, it's the same one-dimensional space, but just drawing above, so that you know what are the area that they share, which is this one. This is the home range overlap between this left and right anima. And this is the home range. Now, as you can imagine, for simplicity, I've taken a set of these, which have the same home range size, and they have the same overlaps. Therefore, there is another one. Hopefully, I do it right. This is the same size, and so on and so forth. So as I was studying, this, when I was in New Mexico, I was studying this problem of, I was involved in studying the problem of hantavirus epidemics, where, there were these rodents which were territorial, or at least there was a home range clearly from the data which was emerging. And so one of the questions at the time, of course, if you have, now the real situation, we know it's like this, no? In 2 dimension, you might have a situation like this, no? A more complicated situation, no? And then, of course, if you're thinking about an infection spread, if you have an animal which is here, which suddenly is infected, then you can ask the question, how much time it takes for the infection to reach here? So it's a spread process. And clearly, if these are confined, then, okay, there are different ways to get there. But what if it's one of those diseases where you need to encounter the animal at the same location? Well, that depends on the biology of the disease. So you may not need to, but then, of course, though this animal, let's suppose we think about this process. So this animal has to roam and reach here, at least within and the other one, which was resident here, I have to also more or less at the same time be there. Then the infection can be passed or not. There is a probability P of passing the infection. And now this is infected also, and then you get to get here and so on. So there is a sequence of events that have to happen for it to go from here to here. And now you know probably that, well, you can do simulation of this process and they take forever. But there are all these SIR, SIER, and so on models, and which allows you to get some understanding, but they all assume that everybody goes everywhere, which of course is not the case. So the time it takes for, if you have an animal here which could go anywhere, but you have another one here and there is no spatial confinement, then it's much different the time it takes to go here. So the question was, how does this affect the speed of propagation, given that everybody is confined? But we thought, okay, we simplify the problem to 1D, and we asked the question, now, in order to pass infection, they have to be at the same place. But now notice, the same place is not just one, just to, because here there could be more than one place. So we just try to think about, well, here there are more than one lattice site where they can meet. So this was the question. Is it clear? So how do you approach the problem? So now I'm going to tell you about first passage, as you have heard me so far. Well, in this context, we were interested in situation where at the most, if you have a right neighbor, let's suppose this is a central neighbor, a central individual, and you have a left neighbor, so given it's symmetric, this overlap, we go to the situation where you have a full overlap, this half of this home range with the neighbor to the left, and half of the home range neighbor to the left. So we didn't go into this moving even further, so that you have encounter of 3 individuals. We just wanted to check only 2 individuals can meet and the pass infection. Of course, you can have an overlap of more than 3 individuals. So, in other words, this overlap, if I call this one L sites, because it's a discrete lattice, and this, I say M sites, so it's an integer, L sites. So we always were interested in M over L less or equal 1/2. So which is this one. At the most, you are in this situation. So in other words, of course, here it's simpler because you just worry about two-way encounter. You don't have to worry about there is a third animal.
M is the overlap?
M is the overlap. So this is, this is half. I mean, this is precisely M over L equal and half. This is the extreme situation we worried about. So now, how do we approach the problem? Now, of course, if we worry only about this, then of course, now you can just think about, I'm going to try to estimate how much time it takes, given an animal infected, to meet the other one to the right. Of course, there will be the propagation also to the left. We just wonder what's happening to the right. And therefore, you need to take into account and find the average time for this animal to infect this one, because then the process just repeats itself. So once you find between two neighbors, then once the right, you have the left is infected, the right gets infected within that average time, then again, you have the same calculation from second to the third and so on. No? So the key point was to calculate the mean encounter times between these two individuals, but it can only be in M sites, not over the entire home range. Is it clear? So now, as I was telling you that before, what I was telling you was you map the problem of two random walkers that are moving and you want to see when they meet into a problem that you have a single random walker in a higher dimensional space. Because these are two random variables that are changing, and now it's a coordinate in a two-dimensional space. Yes?
They both have to be in the same site specifically, or just in the area of the
No, we chose to be at the same site. For this, we are thinking about specific disease where they actually have to meet, and so then. Of course, there are cases that you don't have to. Huh? So now let's go to this higher dimensional space, and let's plot, therefore, let's say from 0 to L. These are all the sites for this one, let's say. And then, now there is this walker, which has its own coordinate. If you want, if I start counting from 0 to L, this will be starting from L minus M to, what is this? This is going to be 2L minus M, no? 2L minus 2M. But, of course, given it's a coordinate, let me just allow me to shift this one. I mean, I can put index here, which is from L minus M to the other one, but I can just reshift, just rename this one. So I know I'm going to have some sort of 0 to L, because that animal has coordinates which range from one number to L, to that number plus S. So if this is A, this is L plus A. So let me just rename it and say the other animal has also coordinates possible from 0 to L. It has L possible sites as well. Now, but where are the meeting places in this graph?
L means 0 to M and L to...
So if I just here, because I have 3 here, they're just now this is a lattice, eh? So let me just...
L minus M.
Yeah, they are here, no? These are corresponding to the possible meeting place of the two. So the coordinates has to be this. So this one for this one, and the other one is here, because it's the first 0 in the shifted coordinates of this one. No, it's the L minus 3 of this one, but it's a 0th of this one. So the first one is this guy here. Now the second one is L minus 2. But then the coordinates of this one is the second one in this shifted reference, because it's the second one here, no? And then the third one is there. Now, if you had the hypothetical situation where you just have two animals and there was a complete overlap, so if you had this situation, then you would actually be the targets, they would be along the diagonal. You would agree, no? So okay, we remember that this we stop at L over M over L less than 1/2. So I mean, whatever L is, so we don't go to that point if you want, but I'm just telling you what the target might be. So once you find where the targets are, then you are in business, as they say, no? Because now you have to do first pass calculation. Remember, the previous hour I was telling you there is initial condition, then there are targets. Now in this case there are 3, but there are M targets. Now you have to find the average time it takes to get from some initial condition to either of these M targets, which is either of this meeting place. So that is going to be your first encounter time. Well, the first encounter time, the mean first encounter time.
Then you have to coordinate between the two individuals.
Yeah, but you know, you're right, but that represents, I mean, you can forget about what the individual were doing. Once you map to the two-dimensional space, now you have one random walker, which has to, you have to ask the question, what is the mean first encounter time, or the mean first passage time to either of these targets, which is the mean first passage time for these to meet. So remember, once you do the mapping, then you can forget about the 1D problem. Then you want to compute here.
Yeah, I mean, because you have two individuals that they have to transmit the disease, they have to be there together. It's not enough just the one individual reaching its target.
Correct. There is a probability P of transmission.
No, there's also a probability of coinciding in the same.
But this is exactly, you know, remember, these are random walkers in discrete time, discrete space. So they're always moving, and they can get there at the same specific time because it's discrete time, no? So I mean, if you have continuous time, you get into problem then because you know there is an epsilon for. I mean, they never meet, no. So you know, this simulation, if you want, you're always doing discrete space and discrete time. Or if you want to be more get into trouble, you create a radius around each of these individual, and then once you know. But that becomes more complicated. So that's why you know we learn in these days about discrete space stuff. So these are important for encounter times. So that you don't have to create radius and do this complicated simulation. So it's what it, please.
About the initial conditions. You have your space now is divided into logically into 2 parts, because you have if they start in one side, so do you take all the initial conditions or just the initial conditions in one side?
You should have written the paper with us. Thank you very much. But so, very good. So we have to take into account the fact that indeed, when you start, you actually start with one infected, and you start here, and you have to roam around to get there to pass. And we did that. And in fact, things changed like a bit. If you just do integrate over all possible initial conditions because you don't know, but in reality you know in this specific problem you know, so you should, and we can do that, yeah, so we're done. So now, before we actually, well, of course I'm not going to show you the math, but so what is the fundamental trick here to solve the problem? So this is the magic. Now it's going to be a graphical magic. Can you believe that? No math. Huh? So graphical magic here. So what I'm going to do, I'm going to think about the problem here. Here you have a reflecting boundary. Here you have a reflecting boundary. Because, you know, remember this is reflecting as well. So, which means that here, so this walker cannot be beyond its own L. And this one cannot be beyond 0 and L. And, so I'm going to make a simple geometry. Because now, in some sense, I have my problem in 2D, and I was saying now there is a confined space, and I could just compute first passage time to the targets. I'm going to make it simpler, the calculation. What I'm going to do, just by symmetry of the problem, I'm going to what they call the unfolding procedure. This I have to say is my collaborator, David Sanders in Mexico. He had this clever idea. So you just unfold the system and then Did I do it right? Probably. Oops. 1, 2, 3. No, I'm missing something here. Yeah, I'm missing something. That's it. So, I mean, I just replicate this on this side, on this side, and on this side. You know, given that this is symmetric, as you know, as I come here, I would reflect. I just allow it to go here, an exact equivalent, and similarly here, it goes the other way and this the other way. So now you have a finite domain with reflective boundary condition. And the targets are here. So you have a big targets, which now has this geometry, if you want. It's a rhombus. And then you have reflecting boundary. So where are the initial conditions? So these are all here.
This is from the second element on, not for the first one.
Yeah, indeed, you're right. In the first time we took in average initial condition. I mean, it's equally likely, but then from the second one, indeed. So, and then this one can, if you want, can up to here. Now, if you are in this situation, I mean, when you are in this situation, then you can actually, this area could just touch this rhombus, if you want. So you have, so now the problem is set, no? So you have an initial.
Why the initial conditions are in the perimeter?
Oh, because you see, these are the targets here, and the animal is, this one, when it's infected from the left neighbor, is going to be here, in this situation. So you have M, remember, this is M targets, there are M targets here. So remember, this is one, these are 3 in this case, so there are 1, 2, 3 here, on this side. So you have, for this, and then due to the unfolding, it's on this side as well. And then what about this? It's anywhere. I mean, this is infected, but where is the other guy? You don't know. So it's all the possible values. And so there are all these possible values, but only, I mean, along this axis, only this M, which, you know, if this becomes larger, because this is becoming larger, no? So there's at a certain point they meet when you are in this situation, when M is as L over 2. But then there are all the possible value for the second walker, which is, you don't know where it is once the left one gets infected, but you know where the left one is. So, okay, so that's a problem now. So, and what we were talking before about first passes calculation, where, you know, it's very similar to what I told you before, no? You have one walker in 2D, there is an area, well, now here the geometry is simple, but there is an area, and then you have a set not just one target, you have a set of targets there. So how do you go about solving that problem? Well, I mean, the real solution is that you write down whatever the master equation in this geometry. But of course, if you look at this, it's not that simple. So, I mean, maybe if this, I would rotate this one would have been simple, but it's not rotate, and you can't rotate it. It's not the same problem, no? But then you can do some approximation, some geometrical approximation. So you think about, there is an area here, and you construct a circle of the same area, centered around here, where now all the data, all the set points here of the circumference are the target points of the meeting place. And then, and you do the same here. Now you have a much simpler geometry. And the area of this is equal to the area of that. And then, what about the initial condition? Well, similar, no? You have another circle for the initial condition, which would be here. So now the problem is you have a circular domain, you have a random walker, which starts anywhere inside here. And you ask the question, what is the first passage time to reach any of these points?
Luca, with this approximation, you lose an important aspect, which it's actually not random or uniformly distributed. There are shorter distances and longer distances. And if he's on the right side and he has to cross the whole territory, so you'll have an underestimation of the real travel distance or passage.
No, you're right. So you do it, I mean, you don't know how much you underestimate or overestimate me, because in one case you underestimate, so it's hard to say, you just do it. And then you compare. So then you do the exact simulation of this problem, and you compare to the approximation. And I mean, it's amazing how they agree. And if you ask me precisely, how is it, what is the reason why they agree so much, I can't tell you. I know they agree. So then now you can use it. It's hard to say, because in some sense you compensate, you overcompensate on one side, and you underestimate. Sorry. So it's. So you're right. I mean, you're right. So we did it, but we were not sure at the beginning what is going to work or not. So you just have to do it. There is not much you can do.
Why do you think there is an underestimation?
Well, I mean, you see, there is this geometry. I mean, remember that the initial conditions are like this. You know, if you are here, I mean, if you make the circle, then this point is very different, you know, than this point here, no? Where you put it. So this is much closer to targets. No? But at the same time, I mean, you see, there is here a double counting of the corner. And as you do the approximation of the double count, so we don't do the double counting of the corner here. We just do the so. So there is another, so you see, they compensate somehow. I mean, we don't get offended. You can say we were lucky. I'm fine. But so it does work.
But why is it so surprising? Because the size, when you saw the how the first passage time is calculated, you saw that it's supposed to be the size of the target and the size of the area. The sizes are what matters.
Yeah.
So there should be some parameter, but
correct.
The same.
Yeah. But the point is that we are talking about those constants that I haven't talked to you. I mean, if I showed you the expression, you're horrified. But this is when you go after the constant, essentially. You're right. I mean, this is true. But then it's really the question of finding the constant. You know. But the beauty of it is that, I mean, if I would have asked you before, what is the dependence on M overlap and size of the home range? Who knows? I mean, we're after that question in particular, in terms of the propagation speed. And if you do this calculation, then you start getting the right answer, because you need to first determine how often they meet, and thus you have to do it right. And apparently this method allows you to do that. Yes?
For the initial conditions, I understand why you take the left side of the dot as the initial condition, but why the top side is also the initial condition?
What did I say?
The upper bound and the lower bound of the domain.
Because
Yeah. So that is, wait,
it can be anywhere on the...
So the L is anywhere. So that's right.
If you think of the second individual maybe being the one that gets the disease from his neighbor, then you need...
No, wait, because did I do right? So this is, L is right, because, so this is M, which is here, and then you get this. Okay, I forgot now. So why is...
You don't know where the disease is coming from.
No, if you don't know, it's in the entire space out here.
No.
It can come from the second individual or from the first. So this belongs to one individual.
Okay, maybe it was the reason. I forgot now. Let me think. Yeah, maybe. Okay. No, good question. I forgot now. But let me think. I think I can tell you, but not at the top of my head. Let me just give me at the end of the lecture. I'll tell you. Okay, I'm allowed to. So. Oh yeah, it's a subtleties. Yeah. I'll tell you later. Yeah. So it's a question. It's a symmetry of the problem, no? So it's exactly equivalent if you go this way or that way. Yeah. Okay. I'll tell you later. So let me come back here. So now we have this geometry. So it's a circular one. So essentially now the problem is this one. These are your initial conditions. And so what do you use in order to solve this problem? Well, in the past, the other day, we were talking about problems where you have a boundary which is reflecting, no? So here it's a bit more complicated because the set of targets, if you write a probability equation, what do they give as a boundary condition? If you're interested in the first pass of problem. It's an absorbing boundary. So once things get there, they get expulsed. They get out of the system, no? So, in the past, in the box, we are talking about you have an animal here, and if these are reflecting boundary, and then you do that, and you do that, and then these tails start to go up, and then eventually you develop that because you have reflection. But if you make the absorption, then you start, and then these, as soon as they get there, they get absorbed. So the value of the probability there is going to be always 0, because as soon as they get there, they're not going to be there essentially. So it's called absorbing boundary condition. So if you remember the diffusion equation, which by now you know, it's d2x2 in continuous space. And then we are talking about dp dx at the boundary, whatever in that case, s plus or minus L/2 equals 0, the derivative. Now this problem is the one where you say p at the boundary is 0.
So the integral will be lower than 1, like the surface?
The integral, you start with probability 1, but then eventually it goes to 0 at infinite time. And it goes to 0 because the space is finite, because eventually you hit here, or eventually you get there. Except this is at 1 point, so then you take an infinite time, no? But as I said before, no? But So in other words, you have to solve the diffusion equation in circular geometry. So you have, if you want, this is a symmetry such as a radial equation. And the boundary condition specific to this problem is that you're going to have, solution, diffusion equation, circular geometry. And so you have two boundary conditions now. It's much more complicated. You have a reflection here, and you have an absorption here. Two which are different. In the box here, these are both reflecting. As you start changing them, things get even more complicated. If you have two different ones, so you have a reflection here. So then you are going to have, for this one, you have a dp dr at r equal this radius r 0. Or this is for this one, and then for this one you're going to have p. Okay, I should put r and t. This is r is radius, t is the time. P of rt 0 at r equal. Let's call this one. Let's call this one r2, and let's call this one r1. These are more horrific expression than the one I didn't show you yesterday. So let me not show it to you. But that's the problem. Now notice that this was a complete discrete situation. We changed the geometry, but now, maybe you have noticed, now I'm talking about continuous variable in time and space. Well, I'm allowed to do that? Well, you're allowed simply because you want to get to some dependencies, and then you have to compare to the simulation. And so of course, as the size of the system becomes large, then you get closer and closer to the discrete solution. 5 minutes. Okay, so 5 minutes. Anyway, so you solve this problem. 5 minutes, what can I tell you in 5 minutes? Okay, let me show you the result. So I want to show you the result. No, what did I do? Oh, this is the unfolding. Oh, you don't see. Is there a way to see view? Is there a way to say view? Oh, there it is, view. Full screen. Ah. Okay, no, it doesn't. Okay, let me just make it bigger. So this is David Sanders. He's an academic, I'm in Mexico. He's a collaborator. He was Sebastian Perez Becker was his master student. Okay, so you see, this is what I was just telling you before. So that's in neat because it's colored now. And so this is a situation where there is full overlap between two territories. This was entirely overlapping, and this is instead of the other possible. This is when you have just one overlap there. Then there is, I told you about the unfolding here. Oh, so that's the unfolding. So you just unfold the system, and then you approximate with the geometry, which is circular. And then you go in and you do your calculation. So, okay, let me just show you this graph. Oop. So, or you were asking about, how far we are from the actual limit, the exact result, the numerical exact when you do the simulation front. And so we...
You compare your analytical model.
Correct.
To the simulation.
So that's, you have the numerical exact. Then this is a continuous limit because remember it's discrete, but then we go into approximating through the geometry in a continuous spatio-temporal situation. And so then, if you look at those, this is when you have uniform initial condition that we just tested, no? On the uniform initial condition, and you see they match pretty closely. Now, do you remember the logarithmic dependence I was telling you about between distance and the target size and the distance? Well, now it's not there anymore. So you can try to check that you get that when the target size becomes smaller and smaller, because now you have the expression which is an analytic expression in the continuum limit, and so you can check that indeed it goes to infinity. As I was telling you, if the size of the target becomes smaller and smaller in continuous space, and then you see, but after some times, after some value of m over L, it doesn't make any sense to use it anymore. You have to use the full expression, and then for the initial conditions which are restricted because of the walker being only, the first walker being on the left-hand side, so which was on that side, then you have to be careful because that's different. Of course, it takes longer. Remember, this is a mean encounter time divided normalized to the home range size. So it takes longer than this curve because you get infected here, and it takes some time for you to get on the other area where there is an overlap. No, there is that time and probably 5 minutes are already gone. No, but let me just show you. So then you use that. Now I don't have the time, but there is a way to take into account that you have a probability because you meet, and then you have to pass infection, but it's not with probability 1. So then you have to compute the return time to either of these possible set of targets. And this is a theorem that you can use by Katz in the 40s, I think, that allows you to do that. And so you have a full expression of that quantity which is, where is it? There it is. So you actually have, you can find out that the mean time for 2 to pass infection, given a probability p which is not 1, if it were to be 1, this term is not there. You don't have to care about return time. But then you have the encounter time, which is a plot I showed you, plus 1 over p, which intuitively, if you think about it, if there is a p probability of infecting, then it's 1 over p, the rate of infection. No? But of course, but then you know exactly, and this again, this has to do with the geometry, and this has to do with the geometry, M and L, and so on. And you can compute that, and then you do the simulation. You now have an approximate way of computing this mean encounter time. And actually, this is the mean encounter time. The mean transmission time between 2 neighbors. And now you compare an exact analytic expression of this propagation of the speed with the simulation of this random walk capacity infection. And this is a curve up here, which has
The dotted lines on the simulation?
Yeah. So these are the various simulations, and you look at the mean is the black line of the simulation. So you're talking about mean, so you would expect to converge, to be close for the mean, no? And so this is the red, let me just check. Yeah, this is a different probability P, let's see. So the thick lines, the thick lines is the thick lines is the average, is the mean, if you want, of the simulation. The thick lines is the mean of the simulation, and the dashed black line, which is, close to the mean of the simulation, is the analytic result. And with different probability P. Okay, so this is just, I'm done. Questions, if you have time. Good, all crystal clear.
The result.
Well, the result is that you can, when you say not mathematical, what do you mean? Yeah, I'm plotting the epidemic position. You have an infected individual. This is an SI epidemic. So then it keeps propagating. And then the infection divided by just normalized to L minus M, and then you see how it propagates over time. So then you have an analytic approximation, and then you have the actual average of the simulation, or the possible realization of the process.